Next, we have Steven Chu, who has a very impressive background. He's a 1997 Nobel Laureate in physics for his studies of cooling and trapping of atoms with laser light. He's a physicist and former government official who served as the 12th U.S. Secretary of Energy under Barack Obama. He's currently the William Canaan Professor of Physics at Stanford University. Today, Steven will tell us about the challenges of getting to net zero GHG emissions. Please help me to welcome Steven Chu.
So, first of all, let me say how delighted I am to have been invited to this wonderful event. It's so far a lot of fun, and with that, let me just begin. I'm going to show you a few things that you're all familiar with, and this I can go through very rapidly. You have seen all this before, but I want to just make 2 points. Number one, this is where we are now. We're not even following current policies. And we just heard a lot about the oceans, 3.7 kilometers deep on average. The bottoms of the oceans, 2 degrees centigrade. The mixing of the surface temperature with the bottom of the ocean is very slow. It takes roughly 50 years. So if you think you're seeing weird weather now, you're not seeing the weather that we've already initiated. You'll have to wait another 50 years if there's no more carbon emissions. Point one. Point two, the World Bank is predicting there may be 200 million climate refugees by 2050. We have seen what 10 million refugees in Europe has transformed the politics of Europe, has transformed the politics of the United States. Now multiply that by 20. And so this is a real issue. So let me briefly outline what it will take. Don't bother reading about this. I just want to make 2 points. Getting to zero emissions. Oh, and by the way, we passed 1.5 degrees centigrade January 2024. 1.5 is past us. And so it means the elimination of steel, concrete, plastics, chemicals, and textiles. It means the elimination of greenhouse gas emissions from the entire food supply chain. And if you consider food production and food waste as a separate entity, it's roughly 30% of global warming emissions. Now, I want to quote someone I started quoting at the very beginning of 2009 when I became Secretary of Energy of the United States. And it was Sheikh Ahmed Yamani who said, "The Stone Age did not end because we ran out of stones. And the age of oil will not end because we run out of oil." Now, let me tell you, that's not why he's the former Saudi oil minister. What he really meant is we transition to better solutions. And you don't think, and you look at rocks on the ground and say, if it weren't for those left-leaning politicians, we wouldn't have these stranded assets. Okay? So we need technically better solutions. And so I'm going to discuss these technically better solutions, but a lot of it is going to be lesson in history. Because, as you know, those who don't know history are condemned to repeat it. And as this gentleman says, those who don't study history are doomed to repeat it. Yet those who do study history are doomed to stand by helplessly while everyone else repeats it. So, a little bit of history. Point number one, all the industrial revolutions that we've been through, materials played an essential role. For example, steel was discovered thousands of years ago, but it was Henry Bessemer who invented the first really scalable method to make steel, the so-called Bessemer furnace. And why did he do this? It was actually for a wartime effort. During the Crimean War of 1853 to 1856, England what happened in the Crimean War? Russia invaded Crimea. Europe said, this cannot be. Sounds familiar? Anyway, England needed a stronger material to replace the cast iron cannons. The explosives were too powerful and they would break. Thence the invention of commercial production of steel. We know all about the invention of the transistor at Bell Labs by John Bartine and Walter Bertin. Bill Shockley, who was their department head, was incensed. And so he took him into his office and said, you know, sometimes the people who did the work may not get the credit. I am going to get the credit. Now, what he did, he was so angry, he holed up for a few days where he was about to give a talk reviewing semiconductor physics and the new quantum mechanics and how it could explain a lot of things. And for that reason, he does deserve to share this Nobel Prize. Okay? But I was a newcomer at Bell Laboratories in 1978, and there was this older guy who was in the office next to mine. And I was wondering, he comes in, he does something. After a couple hours, people visit, then he goes away. I asked my department, who's that guy? He said, you don't know who that is? No, that's Bill Fan. He invented zone refining. Zone refining was a process that enabled Bell Laboratories to make ultra-pure germanium, then silicon, so that you could dope it. And without zone refining, the semiconductor industry would not exist. And so my department head says, so he's Bill Fan. He gets to do anything he wants to do. And he looked at me and said, you kind of remind me of these two young cavemen. They're watching this old caveman walk by, and this one young caveman says, who's that guy? He says, you don't know who he is? He invented the wheel. And the other caveman says, okay, but what did he do lately? Anyway, Charles Kao, Nobel Prize for Optical Communications. Without ultra-pure silicon developed by Corning and then Bell Labs, it would not be a reality. There's a new kid on block of solar that might replace silicon photocells. They're called perovskites. The thing on your right may mean nothing to you. It doesn't matter. All you need to know is that the thickness of this material is 0.3 microns instead of 150 microns. And it uses 90% less energy to produce these cells. And in the last few years, the lifetime is now 15 years, and we think we can make them last 25, 30 years. When this happens, they're going to be twice as good as the best silicon photocells. Okay? So, having said that, we're going to need a fourth industrial revolution powered by carbon-free energy. You all probably know how inexpensive solar energy and wind energy have become, and yet they have to be twice as less expensive than today. And so that's the issue. And so why do they have to be? It's because the full cost of renewable energy means enhanced transmission, distribution systems, backup generation, and storage capacity. And so low-cost energy storage is crucial. Let me show you a picture of my favorite battery. It's the thing on the right. Let me explain how it works. When the wind blows, when the sun shines, you pump water that you might need for irrigation. Okay, the energy is done, it's stored up there on land, and you can open up a valve. 95% of all stored energy is pump storage, lifting water from low to high, let's say from the bottom of the dam to the top of the dam. But geology and geography is not you don't have mountains everywhere, so you need batteries. This is a plot of the energy density per unit weight on the x-axis, energy density per unit volume on the y-axis. That little circle is the Tesla battery. This is where I think we'll be in a decade. Well, how do I know this? It's because I'm on the board. I do battery research in my own lab, but I'm also on the board of directors of a battery company, and we're shipping samples that are there. It will take at least 6 years to get into automobiles because of all the safety issues and concerns. And so the other good news is that the cost is coming down. And what you may or may not know, that there's a law, an empirical law, that says the more you produce, the better you get. Series of incremental improvements gets better and better and better. And so if over a long period of time, the cost comes down exponentially. Could be 5% per year, not per year, but per unit production. So on the y-axis is the number of batteries, 1,000 megawatt hours, 10,000, 100,000 megawatt hours, and the cost is plunging. In 2000, the cost was $2,000 a kilowatt hour. Now it's less than $100 a kilowatt hour. This is commercial costs that automobile manufacturers are willing to pay for a battery, and I'm pretty sure in another decade, $50 a kilowatt hour. But then the question is, there's a question of materials, and there's a question of the mining of these materials, which Jane Goodall pointed out was very, very polluting. And so what do we do? And it turns out that people are beginning to look at how do you recover, for example, uranium, or in this case, lithium, out of seawater. This is Chung Lu. She was a postdoc of mine. She's now an assistant professor at the University of Chicago, and she's doing great stuff. But the point is that we are now looking for non-polluting ways of actually mining these very important materials. All right, let's step back. What do we really look at materials? So as a physicist, I want to step back and look at the big picture. This is the amount of materials we grab out of the earth. And on the y-axis, it's powers of 10. All right? And so on the left, oil, coal, gas, natural, steel. On the right, concrete, asphalt, cement. Okay? The blue in the middle, that's plastic material. But plastics come from oil and natural gas. So most of what we drag out of the earth is fossil-based materials. Okay? What are we looking at? As we electrify, whether it's going to be 50 years or 80 years, don't really know, we will face a copper shortage. And so, what to do? Well, there's a form of carbon called carbon nanotubes, which is actually 1.7 times higher conductivity than copper. There's so much carbon in the ground. And so, can we make carbon nanotubes economical, is the question. We don't know, but all the solutions to our environment and to our energy are about money. And so, if it's too expensive, it goes nowhere. Hydrogen, lots of buzz about hydrogen. If you take natural gas out of the ground, you can turn it into hydrogen and you have byproduct CO2. Burning natural gas or burning hydrogen, which makes water, it is fine, except when you vent the CO2, you're no better off. Blue hydrogen means you take the natural gas out of the ground, you turn it into hydrogen, you take the CO2, and you store it somewhere safely for a very long period of time. But poking holes into the ground, it was discovered actually in those oil and gas fields leak 2 to maybe 4 or 5% hydrogen, natural gas just coming out of the ground. We didn't know this until there was remote sensing, and then found that the estimates from the oil company were too low. All right, there's a new form of hydrogen called white hydrogen, natural hydrogen that occurs in the earth. Preliminary cost estimate, these are really preliminary, is it will be cheaper than hydrogen from natural gas if you don't vent CO2, but we'll see. Many people are beginning to look at whether white hydrogen, natural hydrogen, can be a reality. Let me also remind you that hydrogen is lighter than helium. So given the temperature in the upper atmosphere, they have escape velocity. And yet we know we have hydrogen in our atmosphere. We did not know about helium. We discovered it on the sun because helium just escapes. So we have natural sources of hydrogen that are leaking out. But and the hydrogen would be good. It can be used to decarbonize steel, get rid of the coking process, plastics, chemicals, fertilizer, aviation fuel. But hydrogen is extremely leaky. We don't know whether there are natural rock formations that actually have a big enough reservoir to make it commercially mineable. There's another possibility of iron ores. You put in hot water down there, you change the oxidation state of the iron, and out comes hydrogen. Again, this is untested technology beginning to be looked at. Before you start to install hydrogen pipelines, you have to make sure you can detect hydrogen. But hydrogen has no spectroscopic signature, so no laser detection, no microwave detection, no satellite detection. How do you detect hydrogen? Through mass spectrometry. You ionize the ion in a vacuum and you bend it in a magnetic field. Okay, so you've got to make a mass spec this big that can fit on a drone. There's another way. You look at something that interacts chemically with hydrogen and only hydrogen, and you monitor the chemical reaction. Again, it's got to be this big, light, put it on a drone. So those are some of the technical challenges, which we will figure out. Okay, so even with all this cost-effective wind, solar, utility-scale batteries, hydrogen, we still need compact turn-on sources. And we have a choice. We have coal, natural gas, or nuclear fission. I might say that deployed commercial fusion, in my opinion, is greater than 40 years. I've heard some people say, 20 years. They're thinking maybe the first pilot plant, 20 years, right? So 40 years. Now, the other estimate shared by the person who made the first laser fusion at Lawrence Livermore Labs is somewhere between 40 years and never. Commercial, not as a science experiment. Okay, let's talk about nuclear. People are afraid of nuclear. But if you look at the deaths due to producing electricity, it's led by brown coal, then black coal, oil, gas, biomass, hydropower. Hydropower is dangerous because occasionally dams break. Where is nuclear? Nuclear is down here. It's a little bit safer than wind, a little more dangerous than solar, including Chernobyl, including a couple hundred early deaths in Fukushima due to radiation. What people don't understand is where background radiation comes from, and that a third of the radiation we receive outside of medical procedures, like CT scans, are in the food we eat. Okay? For example, Brazil nuts, bananas, meat, potatoes, carrots. And so, for that reason, there is a unit of radiation that's more understandable to people. It's called a banana equivalent dose, BED. And in Asia, I was telling the South Koreans, you can still use the abbreviation. It's just bok choy equivalent dose. It's a cup of bok choy. Same. And so radiation at this level is not dangerous. Background radiation varies factor of 4 or 5, where you live and what you eat. If you eat a lot of bananas, maybe a little bit higher. But there's no higher incidence statistically of cancer over this range of background radiation. All right, okay. Here's another challenge we need to solve. This is an energy forecast. This is an article written in 2015 of how much energy we're going to use in cell phone technology, in televisions and iPhones and things like that. That's in yellow. And the green is computation, computers. So in 2010, it was 2% of our electricity use. And this article written in 2015 didn't fully appreciate what is happening to machine learning, artificial intelligence. It's insatiable. And so this is a huge problem. The other thing I have to point out is half of compute power in the world today is used in cryptocurrency mining. What's the first application of cryptocurrency? Money laundering. I'm not a fan of cryptocurrency because of the energy. Okay, and machine learning has good and bad. It's fake counterfeits, influencing elections, being used by individuals, countries, and it is an issue, but it also has some very good. I'm not sure about cryptocurrency. All right, we're going to need a fourth agricultural revolution. So another history lesson. This is looking backwards. So on the right-hand side is the present time. This is the temperature estimated from ice core samples in Greenland, Antarctica. For those of you who are experts, it turns out that oxygen, looking at isotopes of oxygen, oxygen 16, oxygen 18, is a very good proxy for measuring temperature. And so you can also measure the trapped carbon dioxide and methane in these glaciers. And what you see is, we're in a relatively warm period, ice age, warm period, ice age, warm period. That other warm period, about 120,000 years ago, the average, this is not a computer calculation, this is history. The average sea level was about 6 to 9 meters higher. How do we know this? Because we look at the fossils of the critters that live in the boundary between the ocean and land, and we can radioactively date them. 6 to 9 meters higher, if we're 1 degree higher than we are today. So, what else? You think, agriculture, it started in the Fertile Crescent, the Middle East. No, it started there, but it also started in North and South China, New Guinea, Ethiopia, all about the same time. In less than 1,000 years, less than 500 years, in fact, maybe. So why did it take so long? Homo sapiens had pretty much a developed brain 100,000 years ago. So let's blow up the history of the recent past. What happened? The climate stabilized. And when the climate stabilized, we started to say, aha, we can grow plants for food. We don't have to be hunter-gathering and roaming around. And so that stabilization actually took enough to start the first agricultural revolution way back when. What was the second revolution? It started in Great Britain. It wasn't technology, a little bit, crop rotation, selective breeding, but a major part was the law of enclosure. You can own land and put a fence around it and keep other people from using the land, which meant there wouldn't be any more overgrazing. The development of markets free of tariffs, custom tolls, barriers, and transportation infrastructure. So it wasn't really science and technology that had to be invented. Selective breeding, magical. Beef cattle, pigs, broiler chickens, the full circumference of the circle is the natural lifetime of these animals, and the red is the time that they're slaughtered from birth. And so we have bred livestock to grow incredibly fast, incredibly efficient. And in the United States, after 24 weeks from birth, a pig will weigh 280 pounds. Okay? So, technologically great. Third agricultural revolution. Well, it was the invention of nitrogen-based fertilizer by Haber and Bosch. It's called the Haber-Bosch process. Fritz Haber got the Nobel Prize in 2018 for this. It was an oversight, so the Nobel Committee decides they're going to give Bosch a Nobel Prize for the Haber-Bosch process. And they said it's for high temperature, high pressure catalysis, which was the Haber-Bosch process. Another well-deserved Nobel Prize. This in peace. Norman Borlaug gets the 1970 Nobel Prize for breeding plants, dwarf strains of wheat that were so much more productive and they could withstand fertilizer, things like this. What's the consequence of this agricultural revolution? There's a timeline from 1961 to 2021. We went from 3.1 billion people to 7.9 billion people. The land put under cereal production did not increase. Cereal production tripled around the world. This was a real agricultural revolution. Okay, so this is some more data on carbon emissions. The world, led by China, is a little bit out of date, but China, followed by the United States, followed by EU plus Great Britain, in its wisdom decided to leave the EU. But if beef and dairy cattle were a country, they would have more greenhouse gas emissions than the US. And so what do? Well, you can consider eating less meat, especially beef. Young people are doing this, and if you really need to think of it this. Poultry has 10 times less greenhouse gas footprint than beef, 10 times. Won't touch tofu, but maybe people don't like tofu. But here's the problem. The fertilizer, we heard a little bit about fertilizer runoffs and the algae blooms and things like that. Most of the problem is you put fertilizer in the ground, what the plants don't use turns into N2O that comes out of the soil. N2O, nitrous oxide, is 300 times worse than carbon dioxide and lasts 100 years. And as we go to more and more people and get richer and have better diets, we will use more and more fertilizer. We have no substitute for fertilizer. Okay? So, what to do? So, I was part of an effort. I was a part of a board of a company that said, if you synthetically alter microbes inspired by legumes and plant it with the corn, these microbes will go up right next to the root boundary of the soil, and they will take nitrogen naturally occurring from the soil and feed the plant. The plant says, feed me, and the microbes say, okay. And this works, except it only works on half the fertilizer, and it's got to work on all the major grains. But it took about 8 or 9 years to develop this partial solution. Too long a delivery time. And so again, that has shaped my own research, because at that time, you can only alter one gene at a time. The solution might require 12 genes. How do you optimize that? Hence 8 years. Hence the company went bankrupt. So, Pivot Bio is still there, but so in my lab, we've figured out a way, we think, to insert a dozen genes all at once, massively parallel. And hopefully we can submit this soon. I said we're likely to go over 550 parts per million, so for that reason, carbon capture from all the point sources, the cement plants, the chemical factories, everything else. But we also need to capture from the atmosphere as well. We emit 52 billion tons of CO2 per year equivalent. And because of agriculture, if nothing else, we'll need at least 10 to 20 billion tons of CO2 capture a year. That's not the last little drop. That's a quarter to a fifth of all our carbon emissions. The scale is enormous. We produce 2 billion tons of landfill waste around the globe. And in 2021, the global production, 8 billion tons of coal, 4 billion tons of oil, 4 trillion cubic meters of natural gas. This is the scale. We have to get as good at putting the stuff back in the ground as we got taking it out. And this is the scale we need. Before we get to this, and before we eliminate all the other carbon emissions, aviation fuel, agriculture, you name it, we got a problem. Okay, what to do? Well, nature's pretty good. It's called solar-powered carbon capture, plants, trees. And reforestation is part of the solution, but the forests mature after roughly 30 years. Then you reach steady state. And so I'm going to propose a novel material in building structures. In all that scale of things, there were two things, energy and stuff that we use to build stuff, buildings, not cars, buildings. And so the novel material is called wood. Structural wood from cultivated forests, not original virgin forests, but cultivated forests can replace steel and concrete. Well, how tall? 3 stories, 4 stories? Nah. Norway has shown you can build 20-story tall buildings with structural wood instead of steel and concrete. Now, here's another thing. Old London has shown us that we can have 1,000-year-old buildings. So in addition to building the buildings, don't tear them down in 50 years or 80 years. Keep them alive. Well, follow Old London. So you've sequestered carbon for 500,000 years, and you're grabbing it out of the ground. And I think the government can really encourage the construction of commercial wooden buildings because steel and concrete is things they're used to, and it's very inexpensive, and it has a huge carbon footprint. Okay, so in conclusion, how long will it take to make a transition from wood to coal to oil and natural gas to what? To green energy and other things, including nuclear in some countries. And in the United States experience, it took, I don't know, about 70 years, okay? But if you look at what's happening in the world, whenever we discover a new source of energy, we just add it. So here you see coal, oil, nuclear, natural gas, and a little sliver on top is renewables and nuclear and hydropower. All right, so currently, we are on a path that will lead us to 3 degrees. I don't know how many people in the audience saw the movie Titanic. You want to raise your hands? Oh, good. Then you remember the scene. These young people up in the crow's nest. They're looking off in the distance, what may look to be an iceberg. So this is an apocryphal story that I'm going to tell you. And they go clang, clang, clang. And it goes down the engine room. All, engines reverse, rudder, turn left, or whatever they call it in nautical language. And the guys up in the crow's nest saying, "Turn, bloody turn! Why aren't we turning?" Because it takes 3/4 of a century to turn. Okay? If it takes 3/4 of a century, why am I concerned about this? It reminds me of the story of an old Nobel person. And he says, "I want trees to be planted." And the gardener says, "But sir, when these trees mature, you'll be dead." And he says, "Then there's no time to lose." Okay, so no pictures except one. This is Earthrise in the right orientation. Anyway, and so what do you see in this picture? You see a barren moon, no air, no water, nothing, not good for life. You see a very beautiful planet. And the astronaut who took this picture said, "We came all this way to explore the moon. The most important thing is we discovered the Earth." Since that time, this is Apollo 8, Christmas Eve, 1968, we have discovered we are altering the destiny of our planet. It's not arguable, except in the United States. And let me also remind you, there is no planet B. Mars has no magnetic field. Without a magnetic field, you will get irradiated very quickly with a lethal dose of radiation unless you want to live underground. And maybe you can find some water and energy, and so maybe you can make oxygen. But hey, we can live underground in the Earth, or we can fix it. So I'm concluding by saying there are some new technologies. We need a little bit more political will and an awareness that it takes so long to turn the ship. And the good news is some of the best and brightest young people are beginning to think, I want to do my career engineering, physics, math, chemistry, political science, law, to help turn the ship. Thank you.